Okay, so there are 8 objectives in ALEX this week that we're going to be looking at, and they're mostly about what we call solution stoichiometry. So this first topic here is calculating molarity using solute moles. So there are a few important things to keep in mind. So molarity is equal to the number of moles of our solute over our volume in liters of our solution. So that's our little formula. And calculating the moles of the solute, often indicated by N, is the mass in grams divided by the molar mass in grams per mole. So that's how we get our moles of solute. Okay, so it's not too bad. So let's see what we've got here. It says a chemist prepares a solution of aluminum chloride by measuring out 147 micromoles of aluminum chloride. So what we know is that our number of moles of our solute is 147. And instead of using the micro symbol, I'm going to replace it with its meaning, which is times 10 to the minus 6 mole. And MOL is the abbreviation for the mole. So that's our number of moles of our solute, which in this case is the ionic compound aluminum chloride. And then that's put into a 350 milliliter container. So that's our volume is 350. And I need our volume in liters for this formula to work. So milli means times 10 to the minus 3. So I'm just going to replace the letter M, lowercase m, with times 10 to the minus 3, and that is the liters. And that's what we're going to make this up to. So what we're going to do is this. A volumetric flask is a long, skinny necked flask with a big bulb on the bottom, and it's got a mark on the side. And when you fill it to that mark, in this case, it's going to have 350 milliliters in there. So what we're going to do is we're going to put our aluminum chloride in the bottom here. And then we're going to add water with stirring until it comes up to the line. And that's it. That's what's going to happen, right? So it says a chemist prepares a solution of aluminum chloride by measuring out 147 micromolars or micromole of aluminum chloride into a 350 milliliter volumetric flask and filling the flask to the mark with water. Calculate the concentration in millimole per liter of the chemist's aluminum chloride solution, round to 3 sig figs. So let's do this. The concentration, which we often just indicate with C, is the number of moles divided by the volume. So we've got 147 by 10 to the minus 6 mole divided in 350 by 10 to the minus 3 liters. But we don't want it in moles on liters, we want it in millimoles per liter. So we need a mole on the bottom there, and then we need a millimole on the top. And in 1 millimole, we get 10 to the minus 3 mole. So there we go. And now we're going to cancel our units before we put anything into the calculator. And sure enough, what are we left with is our concentration in millimoles per liter, just like we wanted, and we're going to round that to 3 significant figures. So it's important that you get used to using the scientific notation feature of your calculator. 147 by 10 to the minus 6 divide 350 times 10 to the minus 3 times 1 on 1 times 10. Helps if you actually hit the button, doesn't it? To the minus 3. There we go. And there we go. It's 0.4. And now we've got to remember that it said 3 significant figures. So 0.420. And we need that 0 on the end because we need the 3 significant figures. and trailing zeros always count in a number that has a decimal point. So there's our answer there. Okay, so the important thing there was, notice how I used the scientific notation feature. So 10 to the minus 3 I entered in as 1 times 10 to the minus 3. 350 by 10 to the minus 3 was 350 e minus 3. You really want to get used to doing that, or you're going to have to put in a bunch of parentheses. You're going to have to hit more keys on your calculator. Just as you move through, it's going to get more and more difficult for you to cope with doing your math without using scientific notation correctly. All right, this looks similar. Something to be aware of is that the symbol uppercase M is often used as an abbreviation for the unit label mole per liter, and this is happening here. So uppercase M indicates molarity, which is moles per liter. So in this case, what we're going to do is we're going to use molarity to find solute moles and solution volume. So molarity is equal to moles on volume, right? Now, molarity, so sometimes people will do N on V. There we go, all right? Molarity is N on V. So you can see from there that molarity times volume will give me my number of moles. And remember, we're going to try and find solute moles. And then finally, we need to recognize, if I rearrange this formula, that the number of moles on the molarity will give me the volume. And so it is always best, it is best practice, and you want to get into the habit of doing this, is to write out your algebra symbolically before you put numbers in. Otherwise, it becomes really difficult for people to follow your work, and also you're more prone to making mistakes. So if you're going to move forward in a professional field that's technical in any way, you're going to drive your boss and your colleagues crazy if you don't do this. Like, people are going to think that you're the most annoying, idiotic person ever. It's just the best professional practice is to do the algebra first, and then you put your numbers in at the very end. And the great thing about it is it'll help you get the correct answer and score well in your tests and quizzes and stuff when you do that. So please, please, please do that. Always do the algebra symbolically, then insert your numbers. So it says calculate the volume in milliliters. So we're looking for calculating volume of a 0.3 mole per liter silver nitrate solution that contains 225 millimoles of silver nitrate. So our number of moles, N, here is 225 times 10 to the minus 3 moles of silver nitrate. And then the molarity of our solution is 0.43 moles per liter, or we can say liter to the minus 1, because remember, 1 on liters is the same as liters to the minus 1. Okay, so what happens here? Well, you can see that moles cancels out, and it leaves me with 1 over liters to the minus 1, which is the same as liters. So this is going to give me an answer in liters. Now, the question asked for the answer to be given in milliliters. So what I'm going to do is I've got to multiply that by the conversion factor that has liters on the bottom and milliliters on the top. And whenever we're doing a conversion using decimal prefixes, the 1 always goes next to the unit label that has the prefix, and the power of 10 corresponding to that prefix always goes next to the base unit. And so there we go, we're going to get our answer. So this is pretty simple. 225 times 10 to the minus 3 divide 0.43, and then that's going to give me my answers in liters, and then I've got to times that by 1 over 1 by 10 to the minus 3. There we go. All right, and so there we are in milliliters, and it asked for 2 sig figs. All right, 2 sig figs. So 520 is going to be my answer here. So 520 milliliters. All right, and if you want, you can put in here 0.523. Okay. Now you see, I didn't round off it at any point. You know, I just put the numbers into the calculator once at the end, and that is certainly something that you should be striving to do. Okay, so in this objective, we're going to be calculating molarity using solute mass. So we know that molarity is equal to moles of solute divided by the volume of the solution in liters. So the difficulty is that we're not going to be given the moles of solute, we're going to be given solute mass. So we're going to take grams of the solute and we're going to turn it into moles of the solute. And to do that, we have to multiply by 1 on the molar mass. Once we've done that, we can then divide by our liters of solution, and then that will give us our moles per liter. So if we read the question, here's our, so what we're doing is a chemist prepares a solution of nickel 2 chloride by measuring out 36 grams of nickel 2 chloride. So there's our solute mass that we're going to turn into moles. So we will be needing the molar mass of nickel 2 chloride. And then it says we're going to put that into a 100 ml volumetric flask and fill the flask up to the mark with water. So this is our volume of the solution. Now, it's important to recognize that this is given in milliliters, so we want to turn it into liters by replacing that decimal prefix with its power of 10. So now we look like we're good to go. We just need one thing, which is the molar mass of nickel chloride. So I'll give you a little warning, is you always want to use a legitimate molar mass calculator if you're going to use the internet to find your molar masses. So I like to use this one from Lentech. If you Google, you'll often get the first answer is not always the correct one, and it's kind of just really awkward. So a good example of this would be AU3Cl6. So here we go, molar mass of AU3Cl6, right? The molar mass is, AU2Cl6, I think it is. Yeah, this one, there we go. It says it's 303.33 grams per mole, right? AU2Cl6, let's have a look at it. AU2Cl6, it's actually 606, right? So be aware of that you know, don't use Google, use a legitimate molar mass calculator. So in our case, we want nickel Cl2 129.60. There we go. So let's see how this works. We've got 36 grams of nickel chloride, and we get 1 mole of nickel 2 chloride for every 129.60 grams of nickel 2 chloride. And so that will give me moles of nickel chloride, and then I know that if I divide that by my volume of my solution in liters, I'm going to get my molarity in moles per liter. So let's go ahead and do that. So it's 36 times 1 divided 129.6. That's my moles, right? So it's 0.278 divided by 100 by 10 to the minus 3. There we go. So 2.8 to 2 significant figures. All right, there we go. All right, so always double check your sig figs at the end. It says here, round your answer to 2 sig figs, so we know we got it right. Okay, there we are. Units are correct, moles per liter. Okay, let's move on. Solving for a reactant in solution. Okay, so this is going to be looking for a chemical reaction. So we're going to need a balanced chemical reaction, and then we're going to be relating molarity, which is moles of solute over volume of solution. And what we can see is if we take the molarity and we multiply it by our volume of solution, you get the moles of your solute, right? So what I'm really saying is that if we have volume and molarity, we basically have moles of something, and that's going to be the key to answering these kinds of questions. So it says sodium hydrogen carbonate, which is this guy, is also known as sodium bicarbonate or baking soda, can be used to relieve acid indigestion. Acid indigestion is the burning sensation you get in your stomach when it contains too much hydrochloric acid, which the stomach secretes to help digest food. Drinking a glass of water containing dissolved sodium bicarbonate neutralizes excess hydrochloric acid through this reaction, right? So it makes carbon dioxide gas, liquid water, and aqueous sodium chloride. The CO2 gas produced is what makes you burp after drinking the solution. So, to suppose the fluid in the stomach of a woman suffering from indigestion can be considered to be 150 mils of a 0.5053 mole per liter hydrochloric acid solution. What mass of sodium bicarbonate would you need to ingest to neutralize this much HCl? Round your answer to 2 significant figures. So what I'm going to do is this. I'm going to take the volume of the HCl. I'm going to multiply that by the molarity, and that will give me moles of HCl. Then what I'm going to do is I'm going to use my mole ratio from my balanced chemical equation to get my moles of sodium bicarbonate. And then finally, I'm going to use the molar mass to turn the moles of sodium bicarbonate into grams of sodium bicarbonate. So I'm doing quite a few things here. So I'm going to need ultimately 1, 2, 3 conversion factors, right? So I'm going to do 3 conversion factors. So the volume of HCl is where I'm going to start, and I've got 150 mils of that. So 150 times 10 to the minus 3 liters of my HCl. And this solution contains 0.053 moles of HCl for every 1 liter. So I have done the first conversion. Now, according to my balanced equation, I'm going to be able to get the mole ratio between the moles of HCl and the moles of sodium bicarbonate. And it's nice and easy in this case. It's a 1-to-1 ratio. So I get 1 mole of sodium bicarbonate for every 1 mole of HCl. So now I've got my moles of sodium bicarbonate, and then finally I've got to multiply it by my molar mass of sodium bicarbonate. So I'm looking to see how many grams of sodium bicarbonate are in 1 mole of sodium bicarbonate. So I'm going to go to my molar mass calculator, and I'm going to go NaHC 0.03, hit calculate, and it'll do it for me. 84.01. 84.01 grams of sodium bicarbonate in every 1 mole. Now look at this. Liters, moles of HCl, moles of HCl, moles of sodium bicarbonate, moles of sodium bicarbonate. The only thing left is grams of sodium bicarbonate. If you're not doing that and cancelling those units out, you're just kind of like setting yourself up to get stuff wrong. You might think you're saving time, you're actually not really. You're just setting yourself up to get stuff wrong. Remember, every question on your quiz or on your test, there's only 20 questions. Each one is worth 5% of your grade. So you want to do everything you can to ensure that things don't go wrong. So I only enter one thing into the calculator, 100 mils, so 100 by 10 to the minus 3 liters, times by 0.053 moles per liter. You don't have to do 1 on 1 because that's just going to be 1, isn't it? But then we go times 84.01. So there's no intermediate calculations. Everything is done in one step. So it ends up being 0.4453 grams. And then we'll just double check and make sure we get the correct sig figs. It was 2 sig figs. So that's going to end up being 0.45 grams. All right, so that makes sense to me. Okay, let's have a look at question number 5. Predicting the products of dissolution. This is not too difficult. When molecular compounds dissolve, you get solvated molecules. When ionic compounds are dissolved, you get solvated cations, and you get solvated anions. Okay. When acids are dissolved, you get H plus ions, and you get solvated anions. So the important thing to recognize is that when some compounds dissolve, namely ionic compounds and acids, you get more than one species present in the solution. So the key thing here is you need to be identifying whether you have an ionic compound, whether you have an acid, or whether you have a molecular compound that is not an acid. So we have to list out everything that is going to be present in an aqueous solution of each of these compounds. And we should also begin by recognizing that there's going to be solvent molecules present in each case. So each of these lists are going to begin with H2O. You don't need to put the physical state symbol there. So iron 2 bromide, that's an ionic compound. So it tells you that it's Fe2+, right? And then a bromide, right? What is this is going to form is every time it's going to break apart to form bromide ions and Fe2+ ions. So because bromine is in group 7A, it forms a 1-, so that will be Br-. Okay, in the next one it says it's iron 3 bromide. So what that means is it's going to form iron 3+ ions, and then it's going to form 3 Br- ions. So it will be Fe3+ and Br-. So because these are all ionic compounds, I know that it's going to form a cation and an anion, right? And I just have to figure out what the cation and anion are. This is iron 2 sulfate. So the iron 2 tells me that it's Fe2+, and then sulfate is SO4 2-. And I just looked up the formula for sulfate anion in a table of polyatomic ions. I knew it had to be 2+ because these guys are in a 1-to-1 ratio. So it's Fe2+, SO4 2 minus. So there we go. All right. So just keep that in mind. Ionic compounds are going to separate out into two things, the solvated cations and anions. Acids will also separate out into two things, hydrogen ions and anions. Molecular compounds, they stay intact. So as long as you keep that in mind, you'll be okay. All right. So this is similar. All right. We've got two compounds here and we have to pick a sketch. So what we know is this thing is being dissolved in water. So most of our diagram is going to be water molecules, right? In both cases, because the water is the solvent, it's the major component. So what do water molecules look like? They have a central oxygen atom and then they have two attached hydrogen atoms. They look like that. Now this guy is ionic. So that means that it's going to separate into potassium ions, which will just be, they're just monatomic. They're just going to look like little spheres. And nitrate anions. And nitrate anions are going to have 4 atoms. So there's going to be a central nitrogen atom. And then attached to that will be 3 oxygen atoms. And because these are just a single negative, they're going to be in a 1-to-1 ratio. So what we're looking for in this solution is that it contains 3 things. Mostly water molecules, they're the solvents, so lots of water molecules. And then a monatomic ion and a polyatomic ion in a 1-to-1 ratio. The polyatomic ion is going to look like this. It's going to have 1 central atom that's different and then 3 outer atoms that are the same. Now, in this case here, the molecule here, it's only got non-metals in there, so that's a covalent or molecular species. So it's just going to look like this, mostly water because that's the solvent, and then there's just going to be one thing present, which are these diatomic molecules of NO, right? So molecules that are made up of 2 different types of atoms. So let's put that all together. Here we've got our ionic compound. It's dissociated into potassium ions. And then these nitrate anions, and they're in a 1-to-1 ratio because there's 1 of each, right? Okay, they combine in a 1-to-1 ratio. Here's our NO, our molecular compound, and we've just got intact molecules that are diatomic, and they're also what we call heteroatomic. The atoms are of different colors there in those molecules to indicate that. All right, now we're going to look at calculating solubility. Now, to calculate solubility is an interesting kind of idea. So here's a big pile of solute, and then we add solvent to it. And what we know is that a solution will be saturated if when it is in contact with undissolved solute, none of the solute dissolves, right? We've got the maximum amount of solution that can a maximum amount of solute that could be present in that solution, right? So if we added more solute in this case, it would just fall to the bottom. It wouldn't dissolve. That's another check. You know, if you add solute and it falls to the bottom, you know that your solution is saturated. So if we have a saturated solution, we can calculate the maximum, you know, solubility, right? The maximum amount of solute that can be dissolved. So that's what these questions about solubility are all about, is you have to ask, do I have a saturated solution? Is that solution in contact with undissolved solute, and is none of that undissolved solute actually dissolving? So let's see what we've got. It says a chemistry student adds a quantity of an unknown solid compound X to 4 liters of distilled water. After 10 minutes of stirring, all of the X has dissolved. So the fact that all of it dissolved tells you that you've got an unsaturated solution. If you added more, it would dissolve, right? It might dissolve. The student then drains off the solution and evaporates the water under vacuum. A precipitate is left behind, The student washes, dries, and weighs the precipitate. It weighs 0.88 kilograms. So the fact that all of the solute dissolved, all of the X dissolved, meant that you were beginning this process with an potentially, unless you were extremely lucky, unsaturated solution. So you can't use this to figure out what the solubility is, right? You need to have a saturated solution in order to do that. Okay. So this question is about understanding how solubility varies with temperature and pressure. So if I think of a solid being dissolved in a liquid solvent, then solubility increases as temperature increases, and solubility is unaffected by pressure. Okay, so that's for a solid in a liquid solvent. For a gas in a liquid solvent, solubility decreases as temperature goes up. So you might have noticed that when you begin to heat water up, well before it starts boiling, little bubbles form. That's the gas leaving, because as the temperature goes up, the solubility of gases goes down. However, this is interesting, the solubility of a gas in a liquid increases as the pressure goes up. All right, so you really have to keep those kind of things in mind as you work through this, all right? So it says, predict what will be observed in each experiment below. 2 250 milliliter samples of water are drawn from a deep well bored into a large underground salt deposit. So NaCl is an ionic compound, and all ionic compounds are solids at room temperature. So we're dealing with a solid dissolved in liquid water. Sample number 1 is from the top of the well and is initially at 42 degrees Celsius. So this is going to be something about temperature. So that's I'm going to call that T1. It's 42 degrees Celsius. And sample number 2 is from a depth of 150 meters and is initially at 8 degrees Celsius. So the one that is, the second one is colder. So what that is really telling me is that it's going to contain less sodium chloride, and this one is going to contain more sodium chloride. Okay? Does that make sense, right? All right. So then now it says both samples are allowed to come to room temperature at 20 degrees Celsius. So I'm going to warm this one up. And I'm going to cool this one down. So if I warm a solution up, it's not going to cause any of the dissolved solid to precipitate out, right? Because it's saturated at 8 degrees Celsius. Warming it up is actually going to make it possible for more to dissolve. So warming up a saturated solution, nothing is going to happen. Nothing happens. But when you cool down a solution from 42 to 20 degrees Celsius, you're going to reduce the solubility, and you would expect solid to come out of solution. All right? Because the solubility at 20 degrees is going to be a lot less than the solubility at 42 degrees. So what we're expecting is that solid might come out of the first one, the warmer one. All right? So it's in a large underground salt deposit, so it's in contact with the salt, so we know it's saturated. Both samples are allowed to come to room temperature, so one gets warmed up, one gets cooled down. a sodium chloride precipitate is seen to form in sample number 1. Exactly. Right. So a bigger mass of sodium chloride precipitate will form in sample 2. No, nothing will form in sample 2 because we're warming it up. A smaller mass of precipitate will form in sample number 2. No, there's not going to be any precipitate because we're warming it up. No, there's not going to be any precipitate. And here's your answer: no precipitate will form, right? Because you're actually going to increase the solubility. So it's going to go from being saturated to being less than saturated. All right, next one. A student sees tiny bubbles clinging to the inside of an unopened plastic bottle full of carbonated soft drink. The student squeezes the bottle. So what are you doing when you squeeze the bottle? You're applying a pressure, right? You're applying the pressure. So what that means when we apply a pressure, when we increase the pressure on a gas in a solvent, more gas is going to dissolve. So we would expect that the gas dissolves. So what's going to happen? The bubbles will shrink and some may vanish. That is consistent with what we would expect. The bubbles would grow and more. No, that would be gas coming out of the liquid. The bubbles won't change. No, something's going to happen. I need more information. No, what's going to happen is we're going to increase the pressure, and that's going to make the solubility of the gas go up. So some of the gas will dissolve into the liquid. All right, guys, so I think that was helpful, and good luck with everything. Yeah. Out of the liquid. The bubbles won't change. No, something's going to happen. I need more information. No, what's going to happen is we're going to increase the pressure, and that's going to make the solubility of the gas go up. So some of the gas will dissolve into the liquid. All right, guys, so I think that was helpful, and good luck with everything. Yeah.